It should smell like cooked marshmallows. Okay. And if you watch, you'll see some bumps start to form in the marshmallows. You'll see a central bump, okay? And then you should see two side bumps also forming. Okay? Now what we need to do is hand me a meter stick. 1 meter stick, please, quickly before the marshmallows catch fire. Alright? What we're going to try to do is we're going to try to determine the separation. Can you guys see we had a lobe here and a lobe here? Okay. We're going to try and measure the separation between those lobes. Now what we saw is we saw some distinct bumps in here, right? There was one clearly right there in the center, but there's also one right over here. Okay. And so what are we getting in here? We're getting a what? Standing wave. Okay, we're seeing a standing wave inside this microwave. And what we're going to do is we're going to try to measure the size of that standing wave. Well, how are we going to do that? We're going to use a
meter stick.
A meter stick. All right.
Of course.
And if I measure that standing wave, I get about 12 centimeters. Okay? So I know that my from maxima to maxima, my standing wave is about 12 centimeters. Okay? That is the first point of information that you need. 12 centimeters plus or minus 1. All right? Is the length of our standing wave. Did you see a standing wave, Brian? Sort of? No. You'll have to do it at home.
I can imagine.
But you can see there's a maxima there, there was a maxima over here. There were actually several maxima. Now, why isn't it a nice linear standing wave? Heat? Because this is not a
Plane wave.
line, right? It's a volume. Yeah? So you're going to expect to get your standing waves not in just a line, but in a volume, right? Is that okay? All right, so what I'm going to do is I'm also going to measure this, and I get about 21 centimeters that way. Oh, wait, I got to go to the top there, and the top is actually 23 centimeters. Okay, so 23 centimeters to the top, and if we go to the inside here, we get about 36 centimeters. Okay, so
What about depth?
oh, depth, very important. Okay, the depth is also almost 36. Okay. Interestingly enough, you notice the depth and the width are almost the same. Okay. It wasn't quite 36, it was more like 35. So this is about 35, this is about 35, and this was about 23. And I measured this and I got just less than 12. Did you notice anything already?
We can know which harmonic is this.
Aha! Aha! Okay, so you've recorded that data. You know the width this way, you know the depth, and you know those 3 dimensions, yes? Everybody's written those down?
Yes.
No.
I'm filming it.
Some person in each group. All right, next thing. Here I have a cup of water. Come on over here, Nick. We need you too. Wait a minute, Jeanette, you're missing all this.
Can't see it. Can't see it anyways.
Well, Jeanette's extra tall. She'll be fine. Okay. Next thing I've got is I've got a cup of water. Okay. Now, the reason I used marshmallows is that marshmallows have almost no thermal mass. Okay. So you can actually see the standing wave because any given marshmallow doesn't absorb very much energy. Is that fair enough? However, if I use water, water is really good at absorbing electromagnetic radiation, right? Marshmallows. If there's a nuclear war, don't shield yourself with marshmallows. Is that reasonable? Okay. Water would be much better to wear a water-filled suit or to go into the ocean. That would be even better. Okay. Okay. So what I've got here is I've just got a temperature sensor. I'm going to measure the temperature of this water, and I get the temperature of this water initially to be 20 degrees C. Do you guys believe that this water is 20 degrees C?
Yes.
Tells us the room is about 20 degrees C. Yes. That's close enough. And if I'm not dead, I should be able to put this in here and get it to go warmer. So as proof your professor is not a zombie. I'm actually not dead. Okay?
Fake Left.
I'll do the other one now. Okay. Yeah. Right. You're still skeptical. All right. So we're gonna stick this. We're gonna put this in here. We're gonna microwave this water for a minute.
Pretty dangerous.
So we have
And I'm going to remove
Power.
everything from this microwave except for the accumulated filth. Okay. And we're going to microwave this for 1 minute.
Over the centuries.
It's microwaving. Hopefully it does not go above 100 degrees. Maybe I better do it for less than a minute.
Seconds.
We'll tell you how long I did it for in just a second here.
do we need to mess up the water?
It is 100 grams of water. You will need to know that. 100 grams of water.
The water blow up in your face.
Okay.
So,
So I have microwaved this, and I am now measuring 57, 58 degrees. Okay, so 57 degrees. So it went from 20 to 57 in 30 seconds. Is that fair enough? Okay. All right. So you have a bunch of data. You're going to need to use that data to
the speed of
do a bunch
light.
of calculations about this microwave. So I'll give you guys that to take home. I'll leave the microwave here. If you wish to use it some more. Sorry? What does the 12 cm represent? Anybody, what does the 12 cm represent? It's the distance from here to here, approximately. I think it was a hair less than 12. But certainly in
I
that...
think 12 is.
12 is a lambda.
Ah, this 12 was also from here to here. This was...
36.
And this was 23. More like 35 and 23. Yeah? Okay. All right.
So we know it's third harmonic. Okay.